welcome everyone to today's Synergist webinar, Knowing Your Risks, PFAS Identification and Exposure Assessment. I'm Kay Bechtold, Managing Editor of the Synergist, the magazine of AIHA. I'd like to thank everyone for joining us today, and especially Velocity EHS for sponsoring this webinar. Today's speakers are Christy Hames, Head of Product Marketing, Chemical Management, and Industrial Hygiene at Velocity EHS, and Lynn Ip, Director and Head of Product, Chemical Management, and Industrial Hygiene at Velocity EHS. Christy brings over 20 years of experience as an EHS professional in the chemical and manufacturing industries, providing strategic leadership in industrial hygiene, product stewardship, ergonomics and safety compliance, and program management. Christy has achieved recognition as a certified industrial hygienist and certified safety professional, and is an AIHA registered specialist in exposure decision analysis. Lynn has over 25 years of experience working in and for multinational companies as well as investment banks. Lynn's experience spans across the spectrum of ESG issues, from social impact and environment, health and safety to chemical management, supplemented with on-the-ground tactical auditing, assessment, and evaluation of industrial facilities. Lynn is a GRI certified sustainability professional. And now I'll turn the presentation over to Christy and Lynn.
Thank you, Kay, and welcome everybody. Good morning, good afternoon, good evening from wherever you're calling in from to join us on the call today, as well as for those who might be listening to the recording afterwards. So for today, our topic is on PFAS identification and exposure assessment. But before we do that, I want to just walk everybody through the agenda of what we're going to be covering today. And as we had discussed before, please do drop any questions into the chat. We'll take them towards the end so we make sure we have enough time to get through all of the material that we need to get through today. So first of all, we're going to go through what are PFAS. This may be a term that you are very familiar with or perhaps not very familiar with. So we're going to do a little bit of level setting before we go into the content. We'll then go through regulatory landscape, where might they be found. We're going to look at how do we assess PFAS in the environment before we talk about potential remediation technologies that are out there in the market. And then finally, looking at how do we assess and control PFAS in the workplace. So before I begin, I just want to share with everybody, myself, I am not a chemist by training. I'm actually an environmental engineer, but I'm naturally curious. And throughout my career, I've been a problem solver. So working with, whether it's manufacturers, working with businesses, working with internal stakeholders, external stakeholders, that's been my bread and butter for most of my career. But 7 to 8 years ago, I was approached by the chemical expert on the team that I was working with at the time. And she came to me with an ask, and which was, Lynn, can you work with me to find out where we might have either present or use PFAS chemistries? And I said, well, what are PFAS? And she said, oh, they're per and polyfluoroalkyl alkyl substances. I can say that quickly today, but I definitely could not say that so quickly when I first was introduced to this. And at the time, there was very little information available outside of scientific journals. And even then, they were just a handful that we were able to get our hands on, and that I quickly tried to understand, read through, try to understand, try to assimilate into looking at how do I apply some of this into the workplaces that we were going in to visit, namely factories and manufacturing processes. So to me, it was almost like what you're seeing on the screen now. It was a jumble of letters. I didn't really comprehend much of it.
Christy, are you there?
I am. Can you hear me okay, Joy?
Yeah, I think we might have lost Lynn.
Okay. Lynn's been having technical difficulties today. Apologies for that. I'm going to try to pick up here until she can get back into the call. So, as Lynn mentioned, she had someone who approached her about looking at PFAS, looking into identifying the presence of PFAS. She was working in the retail industry at the time, and started to look and information that was out there she found some scientific journals and occasional news articles. But it was a very kind of jumble of information, as you see, represented by the Scrabble tiles that you see here on the screen. And really that sums up chemical management in general. It's a lot of information to try to decipher. Going to the next slide. So today, the PFAS, this group of chemicals, has found their way into national newspapers, magazines, social media posts, and it now has its own moniker, which many of you have probably heard, forever chemicals. And the reason they're called this is because they do not break down easily in the environment or in any living animal tissue, plant or animal tissue. And, and Lynn's story is very similar to mine with learning about PFAS. I spent over 20 years in the chemical industry. And really both of us have come to learn that PFAS are not just in things like fabric that's used for waterproofing clothing, as she had in the retail industry before she came to Velocity, but they've made their way into many products. Looking at this graphic here in the right corner, you can see examples of some of the products they're in. For example, shampoos, candy wrappers, firefighting foams, cleaning products, food containers, food packaging, so pizza boxes, microwave popcorn boxes. And it's led both of us on a professional and personal journey to identify where these chemicals may be and how those around us that we work with and in our families could be affected, since they're known to bioaccumulate and biomagnify the higher up the food chain you go. So these graphics here show a little bit of what the bioaccumulation looks like. The first graphic here on the left shows a fish that might eat something, a smaller fish or something that has PFAS in it, and it has a little bit of it that accumulates in its body. But over time, as it eats more things that have absorbed the PFAS, it has a higher concentration of PFAS in its body. And then the graphic that came up in the middle gives a little bit different representation of that, and how it impacts the food chain. So if we have PFAS containing materials in our waterways or in groundwater and in the soil, drinking water, we have it's a PFAS at the bottom of the food chain. The small microscopic organisms might eat it. It's going to stay in their body tissue, and maybe something like a worm would eat this, smaller organism. A small fish might eat that worm. A larger fish might eat the smaller fish, then taking on all that PFAS that is accumulated in the tissues and the food chain below it, then to be eaten by a human or a bird. So you can see how this impacts the food chain.
Hi, Christy. I'm back. I'm so
Hi, Lynn.
sorry, everyone. Some technical difficulties with the Wi-Fi cut out. Thank you very much for continuing the conversation just earlier to lay that foundation. So just picking up from where Christy left off, over the years, there's been a proliferation of international regulations around PFAS, and this has accelerated significantly. Once they were valued for their durability and resistance to heat, water, and oil, PFAS are now recognized globally for their persistence in the environment as well as health threats. And so this has been that shift that's driven a lot of that regulatory momentum that we're seeing around the world. And just here close to home, last year, the EPA announced the National Primary Drinking Water Regulation, or the NPDWR. And that actually established legally enforceable maximum contaminant levels, as well as non-enforceable maximum contaminant level goals for 6 PFAS substances in drinking water under the U.S. Safe Drinking Water Act. We also know that, for example, people who need to report on TSCA, they had issued a requirement for business to report on PFAS usage within their operations, with a start time frame of April 13th next year, 2026, and a deadline for most U.S. companies to have their reports submitted by October 13th of 2026. Of course, there is a small outlier in that if you're a small manufacturer reporting exclusively as article importers, you do have until April 13th, 2027. So these are all, just the show of like what the regulatory landscape is like around PFAS and PFAS reporting. And across the pond over in Europe, the European Chemicals Agency, or ECHA, just published in mid-late August an updated proposal to restrict PFAS in the EU. And they're targeting to complete their review by the end of 2025 to be able to summarize all of their committee decisions to then submit it to the EU Commission in 2026. So again, this regulatory landscape continues to evolve throughout time, and as science becomes more and more available across, not just countries, but also in different communities as well as industries. And in addition to regulatory compliance risks, companies are really now paying more attention to PFAS and trying to find and understand where these chemicals might be in their product portfolio due to the potential civil liability for things like occupational exposure and illness, as well as environmental and health impacts to the community. And these are just some numbers that you see on the screen that we've researched and found. And these impacts can be very devastating to a company. Cost of litigation, we've seen up to $12.5 billion to date in liability. And when we're looking at settlements by claimant, that has anywhere between $75,000 to $375,000 average in settlement per lawsuit per claimant. And that's not even yet considering the cost of human health, right? The bubble right in the middle of the PowerPoint shows over 6,800 cases of cancer diagnoses in the US alone that have been linked to PFAS drinking water contamination. So, companies, they're looking at the risk of financial impact, of brand reputation, of stakeholder relationships. When we're talking about employees and the community, well, having any of these illnesses is a burden on families. It's a burden on community as well as on the governments. So when we think about PFAS, we're also considering, where are those sources and where are those roots and exposures? They will obviously be used, and that's where they were created for, was created for the manufacturing process, right? They were used intentionally for their stability, their water and oil repellency. But when these chemicals get disposed, they take a very long time, like centuries long, to degrade, right? So although you may be removing it from your site and say, well, I'm done, I'm finished with using it, I dispose of it, it's not my problem anymore, it actually becomes a community problem, because once it gets dispersed into the water and soil, these chemistries don't just sit there. They actually will migrate. They then move into waterways, right? Or they get into other pathways that go to, for example, agriculture. They get processed in water plants, to water plants and other food sources. And this then leads it to, being found in not just at work, but also at home. And so if you look at when we talk about the value chain, we think about it not being linear, but rather circular, just as we had seen in the prior slide. What we're trying to show here on this particular diagram is really trying to flesh out, what are some of those general uses that PFAS chemistries have been found in, right? Whether it's in PFAS production itself as a chemical, PFAS uses in manufacturing, in industrial processes, and being also found in consumer products. Similar to, the dial that Christy had talked about earlier, it's found in many, many different types of products. So it's not limited just to, for example, nonstick pans. It's not just about jackets, rain repellent jackets. It's found in cosmetics. It's found in firefighting foam. It's found in deli wrapping paper. So it's found in multiple locations, and the exposure routes then expand beyond just from an occupational side. So if you're working in some of these factories and manufacturing processes, it also then lends itself to being consumer exposure, as well as residential exposure, depending again on the product that's being used. And of course, the ecological exposures to the environment. So what we call, while value chains are circular and not linear, we find that the mobility pathways of PFAS also mimic this circular route and don't stay where they are produced or applied. And so, it goes from where a source of work, where it is applied in manufacturing processes. And we also find it in our homes and eventually, unfortunately, into our own bodies if we're not careful. And so it's getting to know these risks that you have to understand it's beyond the four walls of a manufacturing facility. It's also where is it in our own homes? And that's only if we know where to look for them. And so how and where do we begin to look? And so finding and removing PFAS is very challenging, yet is very crucial for all of us, for all of humanity, because scientific studies have linked PFAS exposure to a number of serious health issues, including those that you see here on the screen. So disruption of thyroid hormones, liver damage, high blood pressure, obviously contamination to the environment, but it's also been linked to a number of different cancers. And we've seen that, for example, a study that was conducted by researchers at Mount Sinai Hospital found that individuals with higher blood concentrations of PFAS had a 56% increased likelihood of developing thyroid cancer compared to those with much lower levels. And so this is a concern for not just the workplace, but as an individual, as communities. Finding and removing those PFAS has very high priority. And it's also then bringing that awareness to, the workplace is trying to say, well, then this is becoming an increasingly important focal point for many companies to proactively determine where PFAS chemistries are within their operations, both to protect their employees as well as to define replacement strategies to reduce, if not remove, the risks to human health and the environment. Because as you can see here on this diagram, chemical management is everybody's responsibility. It's not just a single source, single location. It actually is the entire value chain from beginning to end. And again, it's circular. So there is no beginning, no end. It's actually everybody is involved in this whole process. All right, with that, I'm going to pass the floor over to Christy to talk about how do we assess PFAS in the environment.
All right, great. Thanks, Lynn. When I was previously in the chemical industry, I was very operationally focused. I was a corporate industrial hygienist, but I was also located near our remediation teams and our environmental teams. And, one thing that I saw when working with our remediation team, especially, was that, there were activities that were done in the past prior to environmental regulations that really ended up impacting our organization decades down the road. And, it's something I've been curious about and interested in, my entire career. And the importance of, as new products are developed today, it's not just a matter of looking at how our customers can use this now, how we're going to manufacture it now, but also taking into consideration, how are we safely going to dispose of this? How could this impact the air, the water, the waste, the soil? We don't want to add any more remediation liabilities to our portfolio than we already have. So, one site that I've looked at just for work and also personal matters, just to get an idea of where PFAS contamination could be in drinking water, is this site from the Environmental Working Group. It's interactive. It's available for free on the web. As of last month, so August 2025, they stated that there were 9,500 locations in all 50 states in 2 territories that were known to be contaminated. And one of these is somewhat close to home for me. I live in Central Ohio, and there is a facility in Parkersburg, Ohio, which is kind of southeast Ohio, that had a large settlement with the state of Ohio in November of 23. This facility made PFAS it was actually PFOA, which is perfluorooctanoic acid, and made it from the 1950s through 2013. And they had a lot of contamination in local waterways as well as drinking wells, water systems in people's homes. This is a pretty large settlement that they had with the state of Ohio. It was a $110 million settlement. So this is going back to what Lynn talked about with some of the liability. This is a settlement that didn't end up going to trial. And in this settlement, the money is to be used for creating treatment systems, helping to address the water contamination that's in the private wells, the homeowners' wells, and then also to potentially seek out water sources for some of the impacted areas. In addition to this, they've also paid out millions in personal injury lawsuits. So it's important to prevent things like this from happening. But there is a lot of legacy contamination out there. So if environmental monitoring is going to be done, you can't just sample for sampling's sake. Just like with industrial hygiene, you cannot sample for sampling's sake. You really need to have some goals. So for environmental monitoring, remediation monitoring, you want to track the contamination spread. How far has it gone? Is it localized to your property? Has it gone into adjacent properties? Is it in waterways? And you want to make sure that your sampling is going to then support human and ecological exposure assessments. What are the impacts on the community and the people who live in it, and possibly the people that are in your facility as well. And then you want your sampling to inform your remediation strategies. Now, some of the common matrices where you could find PFAS in the environment, you could find it in surface water, groundwater, sediment, ambient air, rainwater, as well as fish tissue. So when you go to characterize a site for environmental assessment, it's really important to know the site's history. I mentioned the chemical plant before. Knowing it was a chemical plant, it's probably still there, and that it used PFAS, that's important. But there are also things where PFAS are commonly found, places like airports, military bases. Firefighting foam in the past traditionally has contained PFAS. There are substitution products that are being introduced now. But there are old airports and old military bases that had been using those foams for years. Even fire schools could have contamination with them. So what PFAS did they have? When did they use them? How long did they use them? And it's important to know which PFAS compound or compounds that were in use at that site, because that's going to determine which sampling method is used. So things you'll want to look at are the hydrophobicity, that's resistance to dissolving in water, the chain length of the compound, as well as its ability to bind to proteins. All right, so I'm going to do just a very high level snapshot of these environmental methods. I could spend a full webinar talking about these. I do have the sources cited here in my slides. The EPA has a lot of information on this, but I just want to give a general idea of what is out there from an environmental standpoint. So there are two drinking water sampling methods for potable water. This first one here, 537.1, this is for long-chain PFAS compounds, and it measures 18 PFAS in drinking water. The second one, 533, is for short-chain PFAS. This is a little newer standard. It does look for 25 PFAS in drinking water, but it's important to note these two methods combined do not look for every PFAS that's out there. It's also important to note with any environmental sampling for PFAS, and this is true for water and air, that the sample how you handle your samples is very, very important. The containers that the samples get put in for water, they need to be in HDPE or polypropylene containers. You need to avoid any PFAS containing materials such as Teflon tape. Also things like wearing waterproof uniforms or raincoats or footwear that could contaminate the samples. Using the paper that has a coating on it to help it so that you can still write on it while it's wet from water dripping on it. It's important to not use that paper because there could be contamination that comes off into your samples. So they have to be handled very carefully. And then looking at the non-potable water and other media methods, the first one here, EPA 8327, this is for ground, surface, and wastewater. And it'll look for 24 PFAS, like I said, in non-drinking water aqueous samples. So these are water samples, groundwater, surface water, and wastewater. And then the last one for non-potable water is EPA 1633. It was co-developed with the Department of Defense. And this method is best used for looking for PFAS in soil, biosolids, sediment, landfill leachates, and then also in fish tissue. And this can look for 40 different PFAS in non-drinking water or other media samples. Okay, so air sampling, that's still evolving. There are very few validated methods, but there is increasing applicability for ambient monitoring. As an industrial hygienist, I'm obviously very interested in these and how they can relate to doing industrial hygiene monitoring. These are set up as area samples. And as you can see, this is obviously not an ideal way to sample for someone working in the field. This method here, EPA OTM 45, this is going to measure 50 polar, semi-volatile, and particulate-bound PFAS and the air emissions from stationary sources. And these are for things like, what's coming out of the stack. It'll look for PFOA, PFOS. This method can be used to support your TRI reporting. And just a brief summary of what all of it is that you're looking here in this photograph. This is for stack testing, and it uses impingers in series with sorbent resins. It's usually an XAD tube, or there's a front tube and a back tube that will then trap for breakthrough. This method it'll capture both the particle bound and vapor phase PFAS. So this would be ideal for in the workplace if it were small enough and able to be used on a smaller scale for workers. But I'll actually talk about this one a little bit more when I talk about workplace exposure assessment. And then volatile PFAS are collected using evacuated summa canisters. So you'll see over to the right on this diagram is a summa canister, but you have to do a lot of treating to get to that point. This method is for non-polar volatile PFAS and the air emissions from stationary sources. And this method is most commonly used to detect compounds that are released during incomplete combustion of PFAS. So this is testing a stack from an incinerator to make sure that the PFAS materials have been completely combusted. So looking at the diagram here, you're going to have an inertly coated stainless steel or glass lined heated probe that then feeds into the heated filter, which is there to help get rid of and manage moisture in the sample. And then it's going to go into these impingers that are in an ice bath. The purpose of these impingers is to reduce the acid gases to manageable levels so that they don't contaminate or corrode the summa canister or the analytical equipment. And then eventually the sample gets captured in the summa canister. One thing to note, when talking about sample precautions and being careful not to have cross-contamination, I talked about Teflon tape isn't ideal for these samples. The rain-resistant rainwear, clothing, shoes, those are not ideal, but also blue ice. These impingers here are in an ice bath, and it's important to not use blue ice because that could also contain PFAS. And I'm going to turn it back over to Liz so she can talk about remediation technologies.
All right, thank you, Christy. So what we've shared so far, I hope it gives everybody a picture that, PFAS are, forever chemicals. They're hard to break down. There's a lot of different test methods that are available out there to test for their presence. And now I'm going to talk about remediation. And this is still a very growing area around, how we can better manage PFAS. But PFAS contamination itself will obviously pose significant challenges in terms of remediation due to, their strong carbon-fluorine bonds that we've talked about and the fact that they're resistant to degradation. And of course, the potential toxicity to humans and ecosystems. There are quite a number of technologies that have been developed over the, particularly in the last, I would say, 10 or so years. Those technologies have really emerged to address PFAS contamination in soil and water. And each of these distinct mechanisms have their advantages as well as constraints. And they fall broadly in the three main categories that we have shown here: immobilization, mobilization plus separation, and destruction. There's a fourth methodology, which we call the biological method, things like phytoremediation. These are emerging, but still quite limited in scope as well as the scale. Before we jump into the details, I did want to just share with you, in full disclosure, Velocity, we don't do any remediation. We're not in that business, but it is some of the research that I'm just going to share with you in the next few slides is what I've done in terms of working alongside partners as well as industry partners, looking at the whole topic around PFAS and how they can be better managed. So if we go into the next slide, I will just provide everybody with an overview of some of these technologies, just to, again, share the wealth of knowledge. And by no means am I the ultimate expert in any or all of these technologies. So first of all, we have the immobilization technologies, which you see at the top of the screen. These include things like granular activated carbon, biochar, inactivated carbon, etc. And these are really designed to limit PFAS mobility and bioavailability in the soil. It has effectiveness in reducing leaching, the leaching risk in situ in the soils. But while they have been field proven, especially for long chain PFAS, they don't actually eliminate the PFAS. So they restrict its movement, but that restriction of movement only lasts for a limited time. So they also have limited impact on being able to sort of keep short chain compounds from leaching. So some of these particular technologies, you do need to go back and identify, what are some of the more permanent stabilization or follow-up treatments that might be available. In terms of mobilization separation techniques, which is the bottom half of what you're seeing on the screen, these include things like soil washing or membrane filtration. And these remove PFAS from their matrices, whether it's the soil, water, and it's intended to concentrate them for further downstream treatment or disposal. These methods can be effective, but are often limited by the type of soil that the contamination is found in, as well as costs or the need for additional waste management infrastructure on the back end for the downstream treatments. This is typically an ex situ treatment for coarse to moderately fine soils that have a high PFAS contamination. And, the limitation to this or these types of technologies is they have limited efficiency for clay-rich soils. And they also do, in many cases, require post-treatment of the extracted liquid as well as any of the sludge that's generated as well. So again, it's important to understand that there are limitations, there's pros and cons to each of these technologies. And, as Christy mentioned earlier, knowing what kinds of PFAS chemistries you're dealing with is important, not only for determining the testing parameters that she talked about earlier, but also for what kind of technologies you may need to adopt and adapt for the purposes of cleanup for remediation. All right, the third technology that I talked about was destructive technologies. And these include advanced oxidation processes, high frequency heating, catalytic degradation, and these really do target the complete breakdown of PFAS. And these methods have shown promise for the long-term elimination of PFAS burdens, but they can be very energy intensive, very costly, and relative to the other two techniques that I talked about, they are still relatively young in the development of deployment and as well as their deployment. And they're especially in the case of where you have complex settings. So again, it's still being tested out on the field. There's been really good improvements as well as performance, but it is still considered as an emerging technology. The last one that I had flagged for everybody is the biological treatment methods. So we also call biological and plant-based techniques. These include things like phytoremediation and bioelectrochemical systems. They offer what they call low-cost community-engaged options, and they're particularly suited for where the contamination is not, very widespread, as well as not being highly concentrated. But their removal efficiency is limited and varies widely between, both the PFAS type as well as the soil condition. It also, you also do need to consider, in terms of weather, right? In terms of where you're utilizing plants, do they have the right seasons in the locations you're trying to utilize this particular approach to remove PFAS? Because if you have long winters versus long summers, you will definitely get a different performance between those two different regions. So there is slightly lower uptake efficiency as compared to some of the more technical approaches that we talked about just now, and they're not very effective for long chain PFAS. So again, there are opportunities to continue to mature this particular technique, and field studies are still being done, but it is yet again still an emerging approach to PFAS remediation. And in practice, you can probably already guess, there's no single method that is universally applicable to all types of PFAS contamination sites. And really successful PFAS management requires a balance of factors, right? Such as your contaminant profile itself. Like, what kind of PFAS chemistries are we having to engage with? Well, what else are we considering in terms of the site conditions, the regulatory goals, the costs, as well as the sustainability of it? And the table I shared earlier is an at-a-glance comparison table that I'm sharing with everybody here as a resource. But again, it's not extensive. It is just based on the research that we've been doing. And I want to, again, collate it and provide it as a resource for everybody because it consolidates a lot of the key aspects that one would want to consider. Sort of, what's it best used for? What are the key attributes of that particular technology that you might be looking for? What are the pros, the cons, as well as the limitations? And just to wrap up on the PFAS remediation technologies, the four that I talked about, immobilization, is field proven for long chain PFAS, but it doesn't necessarily destroy the compounds. Mobilization is also very effective for source removal, but then it also generates secondary waste. Destruction, it enables permanent PFAS removal, but it's quite costly. And it also could be very infrastructure heavy, depending on the size and scale of the contamination you're having to deal with. And lastly, the phytoremediation, it's low cost and community friendly, but it is slower and tends to be less effective for long chain PFAS remediation sites. So again, just underlining that, the decision making one must take in identifying the right PFAS remediation technology or approach to use, you have to weigh the effectiveness, cost, scale, sustainability, as well as that regulatory context before you can actually determine which is the right solution for you. All right, with that, I've wrapped up the conversation on PFAS remediation. I will pass it over to Christy to talk about how do we assess PFAS in the workplace.
All right, great. Thanks, Lynn. Yeah, so this is probably the section everyone's been waiting for. And I'll mention that this is still a work in progress as far as the industrial hygiene field goes. The main focus of the science and the research has been on the environment. And we're still a little bit behind on PFAS in the work assessments in the workplace. Now, here's our traditional industrial hygiene process. We always anticipate there are going to be hazards there. We're trained to recognize what those hazards are, and what the impacts could be on the worker. And then we're also taught how to evaluate them, control the hazards depending on what the exposures are, and we want to go back and confirm. So really, this is plan, do, check, act. It aligns with the ISO approach. And I have a story that goes along with this presentation that I kind of like to give this narrative as I go through the presentation. And that's that early in my career, I worked at a chemical company, and we were at that time making a lot of chemicals that were petroleum-based, petrochemical-based. And we wanted to be a more environmentally friendly company. We wanted to have more sustainable products. We were looking at water-based technologies. And one day I found out that we had bought the magic water-based technology that was, wasn't regulated. There's no environmental concerns. There were no industrial hygiene concerns. It does amazing things in society and really, helps people. And it was kind of the silver bullet is how it was presented at the time. Now, I was not on the acquisition team for this project. So I was tasked with, okay, we have these new facilities. We're going to be bringing these products into existing facilities. We need to figure out what we need to do for an industrial hygiene assessment standpoint. So I was going to go and do exposure monitoring at all of these facilities so I could quantify the exposures. So I went through all of the SDSs for all of the raw materials and didn't really see any hazards and really any raw materials that had OELs for the chemicals that were in it. I dug through, I thought something just doesn't seem right here with this. I think maybe we had some powders and I was able to do some powder sampling, but when it came to the liquids that were being added to the process, there were no hazards listed. The data sheets were from the original owner. He was a very brilliant man, developed this, technology. His safety data sheets were lacking. This was in the days before GHS, so there were no harmonized statements. It was really a lot of no data available as what was said in each of these sections. So looking back at this now, we didn't have any tox studies, didn't really know what to do with this. Now I look back on this part of my career, which was a long time ago. Some of those raw materials were PFAS. And, I didn't do any exposure assessment for them at the time. And that's probably because there weren't any methods for industrial hygiene sampling of PFAS at the time. And that's still the case. It's very challenging for industrial hygienists. In doing this research, I showed a photograph of this diagram earlier when I was talking about the air sampling. This is the photograph I showed that I mentioned. This is kind of a mess, not really translatable to the workplace, to a worker. We really we don't like putting impingers on workers at all, let alone a water bath full of 4 or 5 impingers. But this EPA OTM method, this is what is done for stack testing. And it involves a heated filter. Then there's a condenser. You'll see the green box there is an XAD tube that's before these 4 impingers in the ice bath, and those collect condensate. And then at the end, in the pink, you'll see there is an XAD tube that collects breakthrough. So, this is obviously not ideal for personal monitoring. The analysis in the lab for the EPA OTM 45 is a gas chromatograph, mass spec GCMS. It also has a pre-concentrator. So, we don't have a method currently that we can do air monitoring with. What do we do? How do we approach this? So when we're evaluating hazards, and chemicals that don't have OELs, our anticipate, recognize, evaluate, control, confirm, it's kind of a modification of that. Several of the steps get combined into doing a hazard and an exposure assessment. So, some sort of qualitative assessment. This one involves control banding, which has its roots in the pharmaceutical industry. It is used to try to look at exposures at certain concentrations and maybe aligning controls with those categories and control band with exposure bands with control bands. This is used in the UK in their control of substances hazardous to health or their cost regulation. And this is in a way we can approach it with PFAS. So the box on the left, hazard assessment. So we want to identify and define what are our hazard criteria. So if we're doing, if we're looking at anticipate, recognize, evaluate, control, confirm, this is anticipate and recognize. So, what are our criteria? Do we have any OELs? Do we have any skin notations? Do we need to look at hazard banding for this? And then we want to do our exposure risk assessment so that we can properly manage the exposures. So in doing the risk assessment, this is evaluation, we want to collect as much information as possible to inform this risk assessment. So we want to look at routes of exposure. Is there potential for inhalation? Is there potential for dermal contact? We hope there's not potential for ingestion, but could someone touch something that has a PFAS in it and not wash their hands when they leave the work area and then go to the break room and eat? So all these things have to be taken into consideration. And then we want to go through, SDSs that we have. Hopefully we have there have been updated for GHS classifications since, I first try to do an assessment. And we want to look for toxicological properties and et cetera. We want to look and see, are there tox studies that have been done? What is out there that we can use for information to help us do this assessment? And then on the right, we have the blue box, exposure management. This is control and confirm. So we want to use the hierarchy of controls to define our controls. And once we've done this assessment and we've determined what our controls are, we're going to reevaluate as necessary. So before I jump in and talk a little bit more on evaluating these potential exposures, the first thing I want to talk about is how do we determine which workers and groups of workers we need to assess. So we're not obviously going to do an assessment for each individual worker in the facility. We want to break them into similar exposure groups. So we want to make sure that we're assessing exposures for people that have very similar exposures in the workplace. So in the case of my chemical plant, I would have wanted to evaluate, you do an exposure assessment for our maintenance technicians. Their work is going to be very different from chemical operators. The chemical operators are doing the day-to-day work in the plant. You know, they're adding in raw materials. Hopefully everything's enclosed. They're doing packaging. Maintenance technicians are a little bit different. They could be doing things like doing some lockout, tag out, blanking, blinding lines, draining equipment so they can do a confined space entry. Or maybe they're taking out a pump to the maintenance shop to work on it for some sort of service that has to be done. So we want to look at each one of these groups' exposures and evaluate what their potential for exposure could be. Lab technicians, they're going to be exposed to lower quantities, but is the work being done in the hood or not? What are they wearing for their protective gloves, eye protection, that sort of thing? So once we've broken down our employee groups into our similar exposure groups, we want to do evaluate the hazards further and what the potential for exposure is to those. You know, since OSHA, I'm not sure how many of you know this, but OSHA and other regulatory agencies, they haven't established OELs for PFAS. I think maybe there are 1 or 2 TLVs for PFAS materials, but that's it. There's nothing for OSHA. And according to the US EPA, there are 85,000 chemicals that are listed in the TSCA inventory that are commercially available in the United States, but only about 1,000 of those have authoritative occupational exposure limits. So this means that fewer than 2% of chemicals in use today have established OELs. On top of that, new chemicals are being introduced faster than IH sampling methods and OELs can be developed, which then creates a major gap in how we manage worker exposures. And this is exactly where this exposure banding concept comes into play. This will help health and safety professionals to make informed science-based decisions for chemicals that lack formal limits. So what is this assessment? It's a form of a qualitative risk assessment for managing hazards in the absence of occupational exposure limits. So how do we do it? Well, as I mentioned before, we want to build a hazard profile for each chemical substance that we're looking at. So we want to look at the GHS hazard classifications. They're going to tell us general categories of harm. Now, SDSs aren't all made the same. They're not all as thorough. One is not as thorough as the next. So we also want to look and see, are there published studies from scientific regulatory bodies? You know, every year there are more and more scientific studies that are published related to PFAS compounds. Can those help you make your informed assessment? Also toxicological information, like no observed adverse effect levels, NOELs, benchmark doses. And then based on this profile that you develop, the chemical is going to be assigned an exposure band. So the bands are going to be A through E. I'm going to go through this on the next slide. And A is going to be the low hazard. E is going to be a very high hazard. And this will give us a science-based way to characterize risk, especially for chemicals that don't have quite the industrial hygiene scientific research behind them. There's some other things, you know, as solvents or VOCs that have been on the market for many, many years. Okay, so once the chemical's hazard band has been created, it's then assigned one of these five exposure bands. So if we look, this is going to be based on how harmful the chemical is, based on the information that you find, as well as the potential exposure. So what this is saying is if you have a chemical that has minimal toxicity effects, even at high exposure concentrations, that's probably going to be an exposure band A. That's the least hazardous. Band B is maybe the chemical has some reversible or mild health effects. Maybe it's an irritant. And this is at moderate exposure concentrations. Band C is a moderate hazard. These are going to be serious or irreversible health effects. And these are going to be seen at lower exposure concentrations. Now, bands D and E are where we get into these higher exposure risks. Band D is going to be something that's highly toxic. It has warnings for severe health effects, and this is going to be at very low exposure concentrations. So maybe this is a process that maybe has a point where a lab tech comes in and takes a sample of it, but there's no ventilation. You're hoping there would be low exposure concentrations, but maybe you need to add additional ventilation to make that a lower exposure. And this last one here, band E, these are things that are extremely toxic, life-threatening effects, and have the lowest exposure concentrations. So the higher the band, the greater the hazard, and the stronger the exposure controls that are needed to protect workers. This system is going to help you to guide decisions, especially for chemicals that don't have exposure limits. Now I'm going to look at control banding. You can see that these colors align, their names align with the exposure bands. And for band A, the lowest risk, we're going to say maybe that needs general ventilation, basic hygiene practices, and also minimal PPE. Band B, you're going to add some local ventilation, maybe a little bit more PPE and some training. C, for those moderate hazards, you're going to keep that local ventilation. You're look at some administrative controls. Maybe it's quarantining off the work area. We know people not being able to enter unless they had a specific training, and maybe introducing some respirators. Band D is going to be more of a closed or isolated system with some more advanced PPE, some chemical suits, possibly some medical surveillance, maybe some blood work. And then band E is full containment, supplied air, or PAPR, and chemical resistant suits. Now, I do want to mention, this approach can be taken for raw materials, individual ingredients, or the entire product itself. It's up to you and your organization how you want to approach this. I would say that if I'm going through and doing an assessment like this, and I have a raw material that contains 0.1% of a PFAS, my exposure band might be a little different than what it is if I have a raw material that has 90% of a PFAS or is 100% a PFAS compound. So the dose makes the poison. It's really important to have your criteria set internally, what your industrial hygiene procedures are and your practices are, how you handle mixtures and concentrations in them, and that'll dictate then what band, exposure band something gets placed in. So I have an example here. This is going to be assuming that we get this chemical coming in and it's perfluorodecanoic acid, PFDA, and we're going to assume that it's 90 to 100% this compound is a raw material coming into my plant. For the exposure banding, I've learned that there's no OEL. Looking at doing some research for the hazard profile, I'm going to see that it can cause skin and eye damage. It's a suspect carcinogen. It has some target organ toxicity for the thyroid and liver. It's also a reproductive toxin and an endocrine disruptor. Looking at some more tox data, there's a low NOEL value. Based on this, I'm going to say this is probably band E or D. There just isn't. This doesn't have an OEL, and we're handling a lot of it. So if I assume high E, the highest, which is band E, and this is subject to interpretation based on your industrial hygiene policies. This for my site, I would say, well, first we need to look if we can substitute a different raw material in here. Obviously, is there something that maybe has less of this this chemical in it, so we can keep exposures low? And then we're going to look at the engineering controls, the closed handling systems, having PPE, that's chemical resistant gloves and suits, tappers. We're going to have some SOPs, work practices for people who are working in these areas. We're going to do maybe just a full medical exam, medical history, and maybe some blood work, do some training. We're going to restrict the access to the area. So, some of the advantages of taking this approach, since we don't really have good air sampling methods and OELs to go off of, it does help to address some data gaps. This will help you also to do some proactive risk assessment. It's better than saying we have nothing, we don't know what to do. This at least gives you a starting point, and it'll help you to be consistent across the board and help to make some transparent decision making. It's also going to help to inform control strategies. You can have some flexibility based on what your company requirements are. You know, I talked about how do you handle 0.1 PFAS in a raw material versus 0.9 or versus 90 or 100% PFAS. And then it's also going to help to strengthen your chemical inventory management. All right, in summary here, just want to wrap up some of the points that we talked about. The first is that PFAS are prevalent across industries and they're biopersistent. They don't break down easily in the environment or the human body, and they're in a lot of places. The persistence is part of what makes them so challenging from an environmental health and safety perspective. Also, the regulatory landscape is evolving rapidly, globally and in the US. What's acceptable today might not be tomorrow. It's important to stay ahead of compliance requirements. Also, the PFAS materials do cycle through the environment. They can migrate through the air, surface water, and groundwater, which makes releases not just an internal issue, but an environmental liability. Let's see, also software can help you identify PFAS. I showed the environmental working group slide of where it could be in water supply. There are also chemical management software products out there on the market that can help you find where those PFAS are in your portfolio. Also, as we look at any kind of environmental monitoring, this is continuously improving. There are some methods that are out there now. Nothing's perfect, but it's getting better. The EPA is a great resource for information on keeping current with this. And then when it comes to exposures, industrial hygiene, we still have some work to do in the profession. So we really need to be proactive to assess those risks and mitigate those risks by doing some sort of a risk assessment in the absence of OELs and sampling methods for most of those PFAS materials. And with that, we can move it over to questions. We have both of our email addresses here if you want to email us directly.
Okay, great. Thanks, Christy and Lynn. It looks like we just have a couple minutes left for questions, so I'll see how many we can squeeze in here. I saw a question that asked, are you able to provide any insight into worker exposures from remediation activities, for example, demolition of buildings contaminated with PFAS?
I don't know if Lynn, if you saw any studies. I didn't see any, but I guess I would look at something similar. Maybe if you have data on VOCs, are you seeing them coming? It's going to be some sort of a risk assessment since we don't have OELs. If you see that there's potential for high VOC contamination and exposures, I would assume that there's going to be some sort of potential for a PFAS as well.
Yeah, definitely say the same, Christy. I haven't come across any particular studies that have alluded to this, but I'll definitely keep my eyes open. If I do come across anything, be happy to share with the individual who may have raised this question.
Thank you. What petrochemical industries would be prone to worker exposure to PFAS?
Oh, this is a very good question. Well, PFAS are, I wouldn't say it's set to any particular segment of the industry because it is used first and foremost. Most of these sites, all of these sites will have some form of fire safety practices, right? And many of them will use AFFF foams. So that in itself is already a source. And so again, this doesn't discriminate in terms of what part or what segment of the industry you're in oil and gas. It is also used in some of the drilling fluids, as well as some tracker fluids that are used for, looking at, where certain extractions may be plugged in for. So again, it's very hard to specify what segments would be, particularly exposed. I would definitely say if you're in the mining and oil and gas industries, is first to understand where PFAS might be used as a chemical within the operations, and then go from there. Because again, it really is dependent on the nature of your activities, as well as the chemical products, as well as firefighting foams that you might have.
Okay, great, thank you. Unfortunately, that's all the time we have for today. Just wanted to let everyone know that we'll be sharing all questions from today's event with the presenters and Velocity EHS. So if we didn't get to your question, we will pass it along. My thanks to Christy Hames and Lynn Ip for their presentation, to Velocity EHS for sponsoring today's webinar, and to all of our participants. Please join us on October 14th for our next Synergist webinar, which will focus on how size-selective samplers impact silica sampling accuracy. You can register at aiha.webvent.tv. Hope everyone has a great day.
Thank you, everybody.
Yes, thank you, everyone. And thank you to the AIHA for having us today. We appreciate it.